8, and so on, probably more like those. Like there are a lot of those are, you use the Euclidean algorithm to compute the greatest common divisor, and so on and so on and so on. They're more algorithmic and computational.
Is there any proofs?
Yep. I mean, as I said in class, so I'm not giving anything away. I would like you to be able to do some of the basic irrationality proofs. That is, that certain square roots or cube roots or fourth roots are irrational without just quoting the theorem, or to prove that certain logs might be rational or irrational or so on. So I want people to do some proofs, but I don't want people to have to do too much. Now, I don't know if you had other questions from that section or.
Not from that section.
I have a question on 25.
Okay, but then I was going to say, well, anybody else have questions? Okay, so from 25, okay. Okay, prove that the least common multiple is the product divided by the greatest common divisor. Okay, well, I don't know how formal an argument you want, so I can go back. Like, I'll start with an example, and an example might be enough. So suppose A was 2 cubed, 5 squared, 11 to the 4th, 17 to the first, and B was 2 squared, 3 to the 4th, 5 to the first, 7 to the 5th, 11 to the second. So here's the factorization of A and B. If we want the greatest common divisor of A and B, for every single prime that occurs in either A or B, you see what the exponent is in the two of them, you always pick the smaller one. So the prime 2 occurs, and if you compare the exponent in A and in B, what's the smaller one? The smaller exponent of 2 is 2 in B. 3 occurs in B, but you don't see it in A. So in some sense in A, you can think of 3 as being raised to the 0 power. So what would the exponent of 3 be if you compare 4 versus over here, 4 versus 0, you could say 3 to the 0, or you could just leave it out. 5 occurs, what's the smaller exponent? 1. 7 occurs in only one of them, so you can sort of think of, in the other one it's 7 to the 0, so you could put a 7 to the 0 there, or that's just a 1, so you can leave out the 7s. 11, what's the smaller exponent? 17 only occurs in one of them, and 19 only occurs in one of them. So that's the greatest common divisor. If we want the least common multiple, for every prime that occurs anywhere, you take the bigger exponent. So the bigger exponent of 2 is, so if I compare A and B, the bigger exponent of 2 is 3. The bigger exponent of 3 is 4, because it's basically 4 versus 0. The biggest exponent of 5 is, biggest exponent of 7 is, biggest exponent of 11 is,
4.
and the biggest exponent of 17 is
1.
And for 19, now, for every prime, when you compare the corresponding exponents, the greatest common divisor picks out the smaller, the least common multiple picks out the bigger. So, if you take the product this would be 2 to the biggest plus smallest. Oops, sorry. A few more symbols here. For 3, it would be the bigger one. For 5, bigger plus smaller, and so on and so on and so on. So notice, since the greatest common divisor always picks out the smaller exponent, and the least common multiple always picks out the bigger exponent, when you multiply, in each case you get the smaller exponent plus the bigger exponent. But if I multiply A and B, I'd be getting the same thing, because for 2, I have to add the 2 exponents, one of which is the smaller and one of which is the bigger. For 3, I have to add the 2 exponents, one of which is the smaller, namely 0, and the bigger. So if you think about it, for every prime, when you're adding these 2 exponents, so for any prime, so again, I'm looking at the product here. For any prime, its exponent is the sum of these 2 things. But if you're adding these 2 numbers, one of them was the smaller one, and one of them was the bigger one. And when you're multiplying the greatest common divisor and the least common multiple, you're again adding the same 2 exponents that you're adding over here. See, so the only real difference is, if I'm multiplying these 2 numbers here versus multiplying these 2 numbers here, I just sort of do some shifting so that the bigger exponent is always going to be on the bottom row. So again, I'm comparing what happens when I multiply AB times what happens when I multiply the least common multiple and the greatest common divisor. Here, these 2 numbers occur, the bigger exponent's on the bottom, so it's the same thing as here, except that I reversed the one that was on the top and the one that was on the bottom. For 3, it stays on the bottom. For 5, the bigger exponent is on the bottom, so it's kind of like reversing the order of this one becomes the top one and this one goes in the bottom. Is that making sense? So I mean, whenever you multiply A and B for any prime, you're just adding the 2 exponents. When you're taking the greatest common divisor times the least multiple, you're again, for every prime, just adding the same 2 exponents. The only difference is here, when I add them, I'm saying I take the exponent of A plus I take the exponent from B. And here, when I multiply these 2, I say I take the smaller exponent and the bigger exponent. But if there are only A and B involved, then when I take the smaller and the bigger, one of them came from A and one of them came from B. So I could give a more formal argument, but I think the informal argument's probably, enough to make it clear. Other questions? Things are slightly trickier with polynomials. They're all almost the same in that when you look at the monic irreducibles, for greatest common divisors, you take the smaller exponents, and for least common multiples, you take the bigger exponents. The only difference with polynomials is you make everything monic. So if we didn't make things monic, there were too many virtually identical answers. I doubt anyone has emailed in a question, but let me just double check. Okay, next question. Yes, Lauren.
Could we look at one of the polynomials? Maybe if we do number 45 in section 12.2.
Okay, do you have the page or?
Yeah, it's page 456.
Okay, 456. Okay, and which one?
45.
Okay. Okay. The situation for polynomials and integers is incredibly analogous. I mean, that's sort of the point that we drove home over and over and over again. So, I'll start off with the case for integers and then come up with the analogy. If you have something like 3 to the 4th, 5 squared, 11 cubed. If I want, so there's the prime factorization of some number. If you want the number of divisors, the number of positive integers that go into it, what we said was you have 5 choices for the exponent of 3, 0, 1, 2, 3, 4. You have 3 choices for the exponent of 5, 0, 1, 2. You have 4 choices for the exponent of 11, 0, 1, 2, 3. So the total number of choices you have for the prime factorization of a divisor is 5 times 3 times 4, or 60. Okay. So whatever this number multiplies out to be, there are 60 positive integers which are divisors of it. Okay. So far, so good? Now, the same thing is true for the monic divisors of a polynomial, assuming it's written as irreducibles. So, suppose you had something like, but one thing we have to be careful about with polynomials is whether something is irreducible or not depends upon where the coefficients are allowed to live. Because something with rational coefficients might be irreducible if you only allow polynomials with rational coefficients, but if you allow polynomials with real coefficients or complex coefficients, those polynomials might become reducible. So if you had something like x plus 1 to the 4th, x squared minus 2 squared, and x squared plus 1 cubed. If I want to know how many monic polynomials, and the reason I'm just sticking with monic is, if a polynomial was a divisor of this, if you multiplied it by any constant, it would still be a divisor. In which case you have an infinite number of divisors and it's a silly question. So we just want to know how many monic polynomials are divisors of it. And since these things are all irreducible in Q, it's the same situation as here. You have an irreducible raised to the 4th power, you have an irreducible raised to the 2nd power, and you have an irreducible raised to the 3rd power. So if a monic polynomial was a factor of this, or a divisor of this, just like before, you've got 5 choices for the exponent of x plus 1. You have 3 choices for the exponent of x squared minus 2, and you have 3 choices for the exponent of x squared plus 1. So just like before, if you're just looking at polynomials with rational coefficients, there are 60 monic polynomials that are divisors of this. Because again, you have an irreducible raised to the 4th power, an irreducible raised to the 2nd power, and an irreducible raised to the 3rd power. So far, so good? But now, suppose I said, how many monic polynomials are factors of this if I consider this as a polynomial in R of x? Well, now things become a little bit different, because in R of x, x minus the square root of 2 is a factor. It wasn't a factor inside of q of x. But if I allow polynomials with rational coefficients, or rather if I allow polynomials with real coefficients, now I suddenly can allow polynomials like x minus the square root of 2 and x plus the square root of 2. So, in here, the situation is somewhat different because these might not be irreducibles. I mean, essentially, we're saying if these numbers weren't all primes, you couldn't use this simple formula. Well, if these polynomials were not all irreducible, you can't use that simple formula. So, over the reals, is x plus 1 still irreducible? Yes, degree 1 is always irreducible. Over the real numbers, is x squared minus 2 still irreducible? Or does x squared minus 2 factor over the reals? Yes, it factors into x plus the square root of 2, still the second here, and x minus the square root of 2. X squared plus 1, is that still irreducible over the reals? Any real roots? Again, if you're down at degree 2 or 3, irreducible is the same as having roots. Once you get to degree 4 and above, they're slightly different questions. So, x squared plus 1 irreducible over the reals. Yes, doesn't have any real roots, because x squared plus 1 is always greater than or equal to 0. So, if I'm counting monic factors over the reals, I need my factorization over the reals. And then, just like before, or similar to before, now I have 5 choices for this exponent, 0 through 4, 3 choices for this exponent, 3 choices for this exponent, and 4 choices for this exponent. Now that ups my answer to 180. So, if I take my original polynomial, but I'm asking how many monic factors are there with real coefficients, I have to check what my factorization is. So can everyone see that once I got this new factorization, where the 180 came from? I just add 1 to each exponent. But now, if I want to know how many monic irreducible factors there are with complex coefficients, I again have the problem of, well, it's not a problem, but I have to deal with, do these things, or have these things remained irreducible? So, x plus 1, still irreducible. It's degree 1. X plus the square root of 2, still irreducible, because it's degree 1. X minus the square root of 2, still irreducible, because it's degree 1. What about x squared plus 1? If I'm allowing complex numbers to be coefficients, is x squared plus 1 still irreducible? No, because what is a root? Right, I and also minus I. So, x squared plus 1 factors into x plus I and x minus I, and since this thing was cubed before, they have to remain cubed. So if I'm looking at the complex numbers, my original polynomial now has this factorization into irreducibles. And now that it's into irreducibles, I can do the same thing. The number of monic factors it has is you just add 1 to each of the exponents and multiply. So now I get 5 times 3 times 3 times 4 times 4, which is 720. So when I looked at this thing, and I want to know how many monic factors did it have over the rationals, there were 60. When I went to the question of how many monic factors does it have over the complexes, I'm up to 720, so the answer has gone up by a factor of 12. And the reason is, the fact that this factored gave me 3 times as many as before, and the fact that this one factored now gave me 4 times as many as before. Now that wasn't specifically the question that you asked, but it was all the ideas. So so for 45, if you're looking for harmonic polynomials, the number 24 doesn't matter in front, because when you're factoring over the rationals, whether you have a constant in front, it doesn't affect anything. So what could throw people off is you might be looking for different ways to factor the number 24. No, if you're factoring polynomials, because remember, when you're looking at polynomials where the coefficients are rational numbers or real numbers or complex numbers, every number is a multiple of every other number. In the integers, 20 is not a multiple of 7. But in the rational numbers, 20 is a multiple of 7. So when you're dealing with a place like the rationals, the reals, the complexes that have multiplicative inverses, every number is a multiple of every other number, so we just sort of ignore the number in front. So if we look at number 45, what we really care about is, if you have something factored into irreducibles, we're just going to add 1 to each exponent and multiply. So for 45 part A, x plus 3 is reducible, x minus 2 is reducible. Over the reals, x squared, or over the rationals, x squared plus 2x plus 3, is that reducible? So x squared plus 2x plus 3, does that reduce? And the answer is no, right? So that's reducible. And does x cubed minus 7 reduce over the rationals? No. So, that's actually factorization to irreducibles. So, the answer to part A is you multiply 5, because that's 1 more than the exponent of 4, times 4, because that's 1 more than the exponent of 3, times 6, because that's 1 more than the exponent of 5, times 2, because that's more than the exponent of 1 over the x cubed minus 7. But for the later parts of this problem, if you're doing it over the reals, you have to take that x cubed minus 7, and over the reals, x cubed minus 7 factors into a degree 1 times a degree 2. The x squared plus 2x plus 3 doesn't have any real roots, so it stays the same. So that x cubed minus 7 splits into a degree 1 times degree 2, so that changes the answer for part B. For part C, that quadratic, x squared plus 2x plus 3, it factors into 2 linear pieces in the complex numbers. And that x cubed minus 7 factors into 3 linear pieces over the complex numbers, because everything over the complex numbers factors into linear pieces. So the answers for part B and part C are significantly bigger than the answers to part A. I don't know if I should do more details or not. Yes?
Could you just go over that for part B? What did you say about x cubed minus 7?
Okay, so the polynomial was, and if you're looking for monic factors in here or here or here, you can ignore the number in front. So we can ignore the 24. So the first polynomial was the first piece.
X plus 3 to the 4th,
Okay.
and then x minus 2 cubed,
X squared plus 2x plus 3.
to the 5th, and then
And this was raised just to the first.
just the 1st.
Okay. If we look at this in Q of x, every one of these pieces is irreducible over the rationals. So over the rationals, the number of monic factors would be 5 times 4 times 6 times 2. Over over the reals, this is still irreducible. This is still irreducible. If you apply the quadratic formula, the discriminant is b squared minus 4 times 3. That's negative. This doesn't have any real roots. So this is still irreducible. But over the reals, this factors into x minus 7 to the 1/3. Because again, if you think about it just saying calculus, the graph of x cubed minus 7, the graph of x cubed minus 7, I just took the graph of x cubed and lowered it 7 units. X cubed minus 7 only has one real root. So it's x minus 7 to the 1/3 times some quadratic. I mean, I could get it from long division, but the point is, x minus 7 to the 1/3 factors out, you get left with a quadratic. You know you get left with a quadratic because there are no more real roots. The other two roots are complex numbers that aren't real. So this is to the first, and this is to the first. So this is the factorization of this polynomial now over the reals, because this split into a degree 1 times degree 2. So now the number of monic factors would be 5 times 4 times 6 times 2 times 2. But now, for c of x, everything reduces into a product of linears. So this was x, the linear x plus 3 to the 4th power, the linear x minus 2 to the 3rd. You could get what this is from the quadratic formula, but let me just call this linear number 1 to the 5th power, linear number 2 to the 5th power. This one was linear. This one splits, this quadratic over the complex numbers is a product of two things with complex numbers, because every quadratic, if you allow complex numbers, is a product of two linears. So this is linear number 3. This is linear number 4. I mean, you might be concerned that when this turns into two linear factors and this turns into two linear factors, how do you know you get the same thing? But the point is, if you look at the two linear factors here, they both happen to be cube roots of 7, and if you look at the solutions here, they're not cube roots of 7. So the two linear factors you get here are different from the two linear factors you get there. I don't know if that was a concern you had, but they turned out to be different. So now this thing has been completely written as a product of linear factors of the complex numbers, and now I just pop one extra to each exponent. So this would be 5 times 4 times 6 times 6 times 2 times 2 times 2. So that's the number of linear factors if you allow complex coefficients. So when you go from Q up to R, polynomials might factor. That means more factors. When you go from R to C, polynomials might factor. That means more possible factors. Questions on this one? So I hope those are the details that you were looking for. Okay, let's do another stop and pause here.